So for part 2 of the problem, we're going to model the system using somewhat of a circuit analysis. So the problem statement says, suppose that the blood leaving the aorta leaves with a pressure of 99 millimeters mercury, and the blood leaving the coronary arteries has a pressure of 85 millimeters mercury, shown in figure 3.2. Assuming that the pressure, flow, and resistance are the same in each artery, Part 1 says, what is the resistance to blood flow in each coronary artery of a healthy individual? Then Part 2 says, what is the resistance to blood flow in each coronary artery of the diabetic patient with the same blood pressure mentioned earlier? And so figure 3.2 is shown here. As you can see, it's a circuit pretty much, with the battery representing the heart. Coming out of the heart, there's a pressure of 100 millimeters mercury going into the aorta. Coming out of the aorta, the pressure drop is 99 millimeters mercury. And after the coronary arteries, which are split up into two parallel circuits, you have a pressure of 85 millimeters mercury. So for the first part of the problem, we know that the mass flow rate is 0.332 grams per second for each coronary artery. We don't know what the pressure is, the pressure drop rather. We don't know what the resistances in the first and second coronary arteries are. And we don't know what the mass flow rate through the aorta is, or the resistance. The relevant equations for this problem are delta P equals the mass flow rate times the resistance, which basically stems from Ohm's law. We have Kirchhoff's constant law, which means that the current coming into a system has to equal the current coming out of it. And also we have the resistance law for a parallel circuit, which means that 1 over the equivalent resistance over both pathways is equivalent to 1 over one pathway plus 1 over the other pathway. And so by using Kirchhoff's current law, we can solve for the mass flow rate across the aorta. And we can do that by saying that the mass flow rate coming into this junction has to equal M1 plus M2, which are the mass flow rates coming out of this junction. And we already know that M1 and M2 are both equal to 0.332 grams per second, because those are the coronary arteries. Therefore, the mass flow rate through the aorta has to equal 0.332 plus 0.332, which gives us 0.664 grams per second coming out of the aorta. So after solving for the mass flow rate through the aorta, we can solve for the resistance across the aorta by using the equation we derived from Ohm's law that tells us the change in pressure equals the mass flow rate times the resistance. And so solving for the resistance, we have the change in pressure divided by the mass flow rate equals the resistance. And looking at this circuit, we can see that the change in pressure across the aorta is 100 millimeters mercury minus 99 millimeters mercury. And that divided by the mass flow rate, which we solved for earlier, to be 0.664 grams per second, gives us 1.51 millimeters mercury times second divided by grams for the resistance. And take note of the unit for resistance in this equation. After solving for that, we can say that the total pressure equals the mass flow rate times the total resistance. And that enables us to solve for the equivalent resistance in this circuit. And so we have the total pressure, which we see in this circuit to be 100 plus 99 plus 85 millimeters mercury, equals the mass flow rate that we solved for earlier times 1.51, which is the resistance of the aorta, plus the equivalent resistance of the coronary arteries. From there, you can solve for the equivalent resistance, and you get 426.2 millimeters of mercury times seconds per gram for the equivalent resistance of the two coronary arteries. From there, using the parallel circuit law for resistance, which tells us that 1 divided by the equivalent resistance is equivalent to 1 over the resistance of both pathways, as you see here. In solving for the two resistances, which are equivalent, you get R1, which is equivalent to R2, equals 852.41 millimeters mercury times second divided by grams. And you can do this because, as given in the problem statement, R1 is equal to R2. And that's because the flow through the coronary arteries is the same. So you can simplify this expression and say R1 and R2 are equal and just write them as 2 over R1 equals 1 over RQ. And since we already solved for RQ earlier, R1 would be 2 times R equivalent. And that gives us the solution for part A. So to remind you of part 2 of the problem statement here says, what is the resistance to blood flow in each coronary artery of the diabetic patient with the same blood pressure? So the solution to that, we start off by writing down what we know. We know that the mass flow rate is 0.027 grams per second for each coronary artery, and that was given in the problem. We don't know, however, what the change in pressure is, what the resistance 1 or 2 through each coronary artery is. We don't know what the mass flow rate through the aorta is, and we don't know what the resistance through the aorta is. Just like in the first part of the problem, the same relevant equations apply. The change in pressure equals the mass flow rate times resistance. Kirchhoff's current law, which is the current coming in, has to equal the current coming out. And also the equivalent resistance rule for a parallel circuit says 1 over the equivalent resistance equals 1 over the resistance through pathway 1 plus 1 over the resistance through pathway 2. So just like in the first part, we solve for the mass flow rate through the aorta first. We do that by adding up the mass flow rates through each coronary artery, and we get that the mass flow rate through the aorta equals 0.054 grams per second. Similarly, the resistance through the aorta, which equals the change in pressure divided by the mass flow rate, equals 18.52 millimeters mercury times seconds divided by grams. From there, we look for the total pressure, which equals the mass flow rate multiplied by the total resistance. Again, if you look back at the circuit, we have 100 plus 99 plus 85 equals 0.054 grams per second, which is the mass flow rate, multiplied by 18.52, or the resistance through the aorta, plus the equivalent resistance of the two coronary arteries. By solving that equation for the equivalent resistance, we have that it equals 5,240.74 millimeters mercury times seconds divided by grams. In the same way that we solved for the resistance through the two coronary arteries in part 1, we do the same for part 2. And we say that 2 divided by R1, since R1 and R2 are equal, is going to equal 1 over the equivalent resistance. And since we already have solved for the equivalent resistance up here, we can solve for R1, which equals 10,481.5 millimeters mercury times seconds divided by grams, which is also equivalent to R2.